There we go. All right, 12.4. We only got 2 more sections left. So stay with us here for the last couple weeks here. 12.4, probability of disjoint and overlapping events. You will probably have to draw some pictures or lay out some different scenarios on your paper before you start throwing numbers in. It's just the nature of probability to help many people out, including myself. But here we go. Compound events. The union or intersection of 2 events. So then a union on the on the left-hand side there, you'll have 2 events happening and then overlapping each other. So they'll include the 2 things happening pretty much at the same time, kind of. Then we have intersection over here. Let's see if this is ready. Great. I don't know where my little toolbar went. Hopefully this will turn up. That's not good. But intersection only the outcome and B have in common. Sometimes they'll have things in common, like you see in this right here. Sometimes they will not have things in common, like you see over here. And we'll talk about what those mean. When it's not, like second example here, when they're not going to happen at the same time ever, that's going to call just disjoint events. Usually down the line, you're going to hear it called mutually exclusive. You'll hear that a lot if you go into any other probability courses down the line, but we'll call it disjoint for now. I'll probably keep trying to refer to it as mutually exclusive, just so you know. But it's when nothing, the 2 events have no outcomes in common. You might only get green today because I'm not seeing my toolbar. I don't really know how to go get it, but we'll just go with it. We have been finding the probability of 2 events happening one right after the other, but now we need to find the probability of one or the other event happening. To find the probability A or B, you need to consider whether the events are overlapping or if they are disjoint. Okay, so here are 2 options. One, they might not be disjoint, and you'll use this first kind of equation, if you will. You'll use the probability of A, add the probability of B, and then subtract the probability of A and B happening at the same time. Why do you do that? Because in these 2, you're including all the events that are happening, but you have to take out the double, like you're doubling yourself over here, because sometimes they'll happen at the same time. And so in this, subtracting A and B will take away those double counted ones. That's what basically that does. So you'll see better in an example. Our second example here, or second formula, is just when they're disjoint. That means you're just going to add the probability of A and B, and that's about it. All right. So it's much obviously easier to see some examples. So let's kind of get down to it. Find the probability of disjoint events. So we're going to use that second one. My opinion, the easier of the 2, just because you're adding the 2 probabilities up and finding your answer. A card is randomly selected from a standard deck of 52 playing cards. So you're going to have to know a little bit about cards in order to understand some of these problems. What is the probability that it is a 10 or a face card? What is a face card? King, queen, or jack? Okay. No, ace is not a face card, just king, queen, or jack. Let's see, probability that is a 10. Well, how many 10s are there in a deck? There's a 10 of hearts, 10 of diamonds, 10 of spades, 10 of clubs. So there's 4 out of 52 10s, right? There's 4 10s in a deck. If you need a deck, like a physical deck, go grab one at your house and count how many 10s there are. How many face cards are there? Well, there's, like we just did, there's going to be 4 kings, there's going to be 4 queens, and there's going to be 4 jacks, right? Of all the different suits: hearts, diamonds, spades, and clubs. So there's 4 of each, just like there's 4 tens. There's 4 kings, queens, and jacks. So add these up, and you'll get 12. Those are 12 cards of those out of 52. And these are disjoint events, so we're going to be using that second equation over here, all right? Using that second one because it's a disjoint event. Great. We know it's disjoint because, well, there's never going to be an overlapping point where you draw a 10 that's also a face card, right? They're two totally separate things. So that's why it's disjoint. So when you add those fractions up, you get 16 over 52, which is about 30.8%. That's it. Great. I really want another color. Oh, we're not going to get it. Disappointing. All right, two 6-sided dice are rolled. What is the probability that the sum of the numbers is 4 or is 5? Well, what are the chances? How many chances are there that we roll a sum, right, of 2 dice? We found that when we did like 1, 2, 3, 4. We did that whole chart over here, right? 2, 3, 4, 4, 5, 6, right? We really have 36 combinations. It's a 6x6 grid. So there's 36 possibilities, right? 1 and a 1 is 2, right? A 2 and a 1, right, is 3. Oh no. I lost my clicker. Let's see if I can go find it. Tools. Tool. Come on. Yes. Oh, money. Cash money. And I can do another color. You know I'm going that other color. All right. 3. A 1 and a 2 is 3. 3 and a 1, this is what we care about. 4. A 2 and a 2 is 4. A 1 and a 3 is 4. 1 and a 4 is 5. 2 and a 3 is 5. 2 and a 3 is 5. And 4 and a 1 is 5. So we know, right, if I want to roll a 4, I have 1, 2, 3 possibilities. I roll 4 out of the 36 possible outcomes. What's probability to roll a 5? 1, 2, 3, 4 out of the 36. Now I just add those up. 7 out of 36. I didn't do that in my calculator yet. Let's see. 7 to 36. It's about 19.4%. And that's it. Great. Let's move on to the other type, probability that of overlapping events. And what you could do with some of these if you really wanted to is make a Venn diagram. The 2 circles and they overlap. That's what they mean by overlapping. And we can draw pictures to kind of help us decide what's what. These problems. A card is randomly selected from a standard deck, 52 playing cards. What is the probability that is a face card? We know what those are now. Or a spade. So there's 13 cards in one suit, right? The spade, club, hearts, diamonds, all those, right? So probability of A is going to be our face card. What's the probability it's going to be a face card? Well, those are king, queens, or jacks, right? And there's 4 different suits. There's the spades, clubs, and diamonds, hearts. So we'll have hearts. We'll have, I'm not going to draw all these because these are kind of funny looking. Clubs, right? Those look like those. And then, what's the other one? Diamonds, right? That's one possibility, but there are ones that are spades, king, queens, and jacks. right, that are spades. That's the other shape. I can't draw it very well. But then the other side, we have spades. These are all just spades over here, right? These are face. Not sure face. So 10, 9, 8, 7, 8, 6, 5, 4, 3, 2, 1. Or sorry, 2, 8, right? So there's 10 over here. I don't know if I can draw them all. 8, 6, 5, 4, 3, 2, 8. Great. So there's 10 of them. And so then there's 1, 2, 3. Oh, sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right over here. All right, great. What's the probability that is a face card? So there's 9, we just counted, out of 52, plus the spades, we just counted over here, 10 out of the 52. Oh. Did I do that right? Let's see. I understand. I did it wrong in my side notes. There's 9 separated, right? I guess you could do it two ways in that case, but I'll show you what I mean. You have 9 over here, right? But then you have 3 right here you can count in, right? Because these are also face cards. So technically there are not 9, but you add 3 more would be 12, right? Same thing here. You add 10, but then those there are 3 more king, queen, jack spades, so it'd be 13. Then you're technically subtracting, right, from our first equation over here. I'm talking about this one. Probability of A, probability of subtract, probability of B, subtract probability of A and B. That's that middle section I was just referring to. Subtract 3 from this whole thing because you don't want to double count these in both, right? That 3 will discredit the double counting that we just did. So let's see, it looks like it's 22 out of 52. Let's put that in the calculator. 22 out of 52. Looks like it's 42.3%. It seems kind of big, but I think it should be right. Okay, very good. Now, what you could have done, I guess, is just, let's see, what would you have had to do if you're doing it that other way? 9, 10, and then I guess you would have added 3 out of 52, but like I said, you should add up all this stuff right here, add all of this stuff on the other circle right here, and then subtract whatever's in the middle. That's what the formula calls for, really. So that is a way to do it. Now, you could do it just by counting, like we're going to do in this next one. The bag contains cards numbered 1 through 20. One card is randomly selected. What's the probability that the number of the card is a multiple of 3 or a multiple of 4? Okay, so multiples of 3. 3, 6, 9, 12, 15, 18. Nice. Multiples of 4. 4, 8, 12, 16, 20. All right, so these are all the possibilities, right? Or, A, B, right? This would be A, this would be B, right? Probabilities. And there's 20, so we know it's already going to be out of 20 different cards. Okay, so we have 1, 2, 3, 4, 5, 6, plus 1, 2, 3, 4, 5 for B. How many are doubled 1. So you subtract 1 out of 20 from this. All right, hopefully that one helped make more sense of why we did what we did at the top. All right, so it looks like we have 10 out of 20, which means we have a 50% chance. Drawing multiples of those two. The 3 or multiples of 4. Nice. Okie dokie. Okay, so this is going to be a little bit of re-engineering our formula here for A and B. So it looks like we're going to use that first formula that we have at the top there. We're going to have a overlapping event, but we're going to find A and B, the thing that we subtracted at the very end. So our formula went probability of A or B equals probability of A plus probability of B, and subtract the probability of A and B. So this is the thing we're going to be finding at the very end here. Out of 200 students, so we already know the whole thing is going to be out of 200. 113 students are either varsity athletes or honor roll students. That's bing, 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 A or B. Done. Got it. That keyword, right, is super helpful. There are 74 seniors who are varsity athletes, the probability of A, right, are varsity athletes. So 74 divided by 200, because there's 200 kids. The 51 are seniors. That's the other probability, so 51 divided by 200. And then we're going to be finding this. We don't have to read the rest, but we'll read the rest. What is the probability that a randomly selected senior is both a varsity athlete and a honor roll student? Okay, so probability of A and B. Okay. So now we just kind of use our, just use some good fraction adding, subtracting skills. Add these up, you should get about 125, and then you subtract that from the 113, and you'll get a negative number, right? But this is going to be negative anyway, so they're both going to turn positive. At the end of your subtracting fractions, you should get 12 out of 200 on one side, and the probability of A and B, I'll just do that for now. And go. And then you punch it in a calculator, and you get 6%. Not 60%, 6% equals that. That they're going to be both a varsity and honor roll student. Sweet. And this also means that 12 out of the 200 were both varsity and honor roll. Nice. Okay. Here comes another one. Out of 45 customers, a breakfast cafe. This is the same stuff, right? You have 45 customers total. 42 either bought orange juice or coffee. Coffee or orange juice. So 42% of them, 42 of them bought one or the other. Or even both, right? Equals probability of A, orange juice. 30 customers bought orange juice out of the 45. 40 customers bought coffee. So obviously, if you're looking at these numbers, they're like, oh man, a lot of people should have bought both at some point, because that overlaps the 45 total customers. So a lot of people did both. What is the probability that they bought coffee and orange juice? All right, so subtract probability of A and B. Yeah, I'm running out of room here. I don't know how much more room you have than I do, though. All right, so add these together. You get 70 out of 45 equals 42 out of 45. Here. Minus probability of A and B. Right, subtract 70 from 42, and you get negative whatever, 38, 28. But the other side has a negative right here, right? So you're just going to cancel both those out. 28 out of 45 equals probability of A and B. Punch in your calculator, you should get about 62%. Yeah, and like I said earlier, you can already kind of tell, wow, there should be a lot of people that did both. So looks good. All right, there's actually 2 more slides here. There's going to be one more problem that I want you to see because it might be on the homework. So just stay tuned. Identify the events as disjoint or overlapping, then find the probability of requested. So we're going to decide whether it's disjoint or overlapping and then find the probability. Card is randomly selected, standard deck 52, playing cards. These are not including jokers, by the way. Find the probability of the events. Ace or 8. Well, you can't draw an ace that's also an 8, right? So we know there's 4 aces in a deck. We know that there's 4 aces in a deck, right? If you can't draw both an ace and an 8 at the same time, right? This is disjoint, clearly. Great. Blech. Terrible handwriting. All right, well, looks like it's 8 out of 52 chance that you draw one or the other, and I got 15.4%. Cool. Different color. Boom. Select a 10 or a diamond. Well, a 10 could be a diamond, 10 of diamonds, right? So you would want to say that this is overlapping. Okay, that's step 1. So you know they're going to include both. So I guess if you don't want to draw the Venn diagram, you could, if you wanted to, draw all the, 10s there are and how many of the diamonds there are. But if you know cards, you know that there's obviously 4 10s in the mix out of 52. You know that there's how many, then you got to count, or if you just know, right, how many diamonds are there in the deck? Well, each suit is a fourth of the deck. Well, a fourth of 52 is 13. Some people just know that there's 13 of each suit. 13 cards of each suit. King, queen, jack, 10 through ace then, right? That adds up to 13. And then you're double counting, right? This is the overlapping one. So we have to subtract A and B, probability A and B together. There's only one 10 of diamonds. So we just subtract 1. No, we don't subtract 2, including both of them. Some people might think that, but we only subtract 1 because we only want to get rid of 1 double counted, right? We don't want to get rid of 2 double counted. Then we're discrediting the 10 altogether. That'd be silly. All right, so looks like it's 17 minus 1 is 16 out of 52. And we've seen that one before. It was like 30.8% of selecting 10 or a diamond. Nice. Okay, there's one more. And it's not in your notes, I understand. But you might see in the note in the homework. It's a little off kilter of what we've been talking about in this little section, but I wanted you to be prepared in case this is a case. Otherwise, it's good to know because you'll run into this in other probability classes. This is a mouthful, so let's read it fast. Using tree diagram, find the compound probability. We are going to use a tree diagram on this one, so stay tuned. American Diabetes Association estimates that 8.3% of people in the United States have diabetes. Suppose that a medical lab has developed a simple diagnostic test for diabetes that is 98% accurate for people who have the disease. That's going to be important. 95% accurate for people that do not have the disease. That's also important. So diagnostic is just telling you whether, you got it or you don't. The medical lab gives a test randomly to a randomly selected person. What is the probability? We're assuming that this person's in the United States. Well, yeah, in the United States. Yeah. What is the probability that diagnostic is correct? So what we're going to do is draw a tree diagram and then follow the branches of what is correct. So U.S. Citizens is at the top, right? I'll just write sit. You have a probability that they have the disease. So 0.083, right? That's at the beginning. It said 8.3% of people in the United States have diabetes. On the other side, you have 0.917 because you're subtracting that from the 100%, right? These are the people that that do have it. These are the people that do not have the disease, right? Okay. So it also said that people that who have the disease, right, who have it, the success rate of the diagnostic is 98%. So, who did I write that on? Who have the disease? Oh, who have the disease, right? Who have the disease. So we're following this column over here. 98% of people who have the disease, right, will get tested correctly. But there's a 2% chance that those people will not get diagnosed. The diagnostic will not be successful, right? Correct. Incorrect. Pretty good success rate, in my opinion. Okay, on the other side, people that don't have the disease, right, do not have it, said 95%. So we have a 95%, which leaves the rest of it being 5%. Right? Oh, that doesn't need that. Right? So that's as far as we go. Right? If we want to find the success rate, we have to add the probability that it's successful on. I'll highlight it. Let's just do this. We have to find the success rate of people that do have it over here and multiply it by this, right, to find that success rate. But then we also have to add that to the success rate over here as well. Okay. So that's what they're looking for. So here's our formula. If you follow it, great. If you are still struggling in this one, I get this one's a little more confusing. I'll grade this a little with a fine-tooth comb here and kind of show some grace in that realm, because I get this is a little confusing, especially online. But here's the formula that here's the equation we're gonna follow here. So 0.083 times 0.98. And we're gonna add, I ran out of room, the other stuff, right? The other side of the tree. And sorry, if you don't, what I was going to say, if you don't get quite where we're getting some of these numbers, or at least like where the formula is coming from, just kind of use this as a guide for some other problems and see if that helps. If it doesn't, like I said, I'll use a grace kind of period of judgment to give you what you need to get out of what we're doing here. All right, so we're going to put all those things, we're going to multiply these two, we're going to multiply these two, and then add them up. That's how we're following this. Once you do that, the diagnostic should have a 95.2% success rate for both people that do have the disease and who do not have the disease. And that's what it means by compound. You're combining the two probabilities together in a sense. Great. That is 12.4.